Stripping down science. The Naked Scientists.
Now, is it better to blow up an Earth-bound asteroid or to leave it intact? This week we're answering that and more of your science questions. My name is Chris Smith. Then also with us is Dominic Ford and Diana O'Carroll. Hello, Diana.
Hi. Also on the way, is it true that people look in a certain direction when they're lying? Plus, we've got a challenge for you with our kitchen science this week. Dominic.
Yes, Hugh Hunt from the University of Cambridge will be joining us to test your ball skills.
Got a bouncy ball, and I'm on one side of the table, you're on the other. Now you've got to catch this ball.
I'm ready.
Floor.
I'm ready. Oh, well, that's hardly fair, is it?
If you want to have a go at that experiment, and you will be impressed, I don't mean that in a dictatorial way, you will be impressed by what you see, because you'll understand why Frank Lampard failed to score at the World Cup in 2010. You just need a bouncy ball and a table to have a go.
The Naked Scientists podcast is powered by UK Fast, the UK's best hosting provider. On the web at ukfast.co.uk.
Paul Winter got in touch with us and we phoned him back, and he has an interesting question, I think, for you, Diana. Hello, Paul.
Hi, Chris.
Fire away.
Hi. I know that alcohol is a diuretic, but if one was in a situation maybe stranded at sea and all you had to drink was maybe something like beer, would it be worth drinking the beer or would it just hasten dehydration?
What brand of beer did you have in mind, more importantly?
Any beer.
Diana?
Well, the answer is yes, it probably is okay to drink the beer as long as its alcohol content is less than 10%. So if you're not going for the things like Special Brew and the really sort of hardcore beers, then you're probably actually going to hydrate yourself rather than dehydrate yourself overall. And another little tip is that if you do perhaps only end up with wine or something that does have more than 10% of alcohol in it, then maybe if the temperature's high enough, you might be able to undo the top, leave the alcohol to evaporate a little bit, and maybe reduce the overall alcohol content. You might have something, well, it won't be very nice to drink, but it might save you. You never know.
So there's a threshold concentration at which we think there's a beneficial effect of about 10%. Beyond that, people are going to dehydrate net, but they'll have some fun. Under that, then probably you'd be okay to drink it and it will do you a benefit. Yeah,
that seems to be the case. And also a little factoid, in the medieval period when fresh water was just so horrible to drink, everybody used to drink small beer, which was very low alcohol beer, and obviously they didn't all sort of become desiccated and dried out like prunes, so it must have worked.
Yeah, I remember reading, when you read archaeological texts and things and you see that the people building Hadrian's Wall, for example, were being given a ration of beer every day, and it was largely all they were being served. And I remember thinking when I was little, gosh, weren't these people permanently drunk? But it's because the alcohol content was low.
Yeah, that's right, yeah.
Super. Paul, does that help you out? So you know what to do if you're lost at sea in future?
Yes, that's really good. Thank you very much.
Actually, Hugh Hunt, who is with us today to do our experiment, you heard him in the introduction, he actually had an extra point to make, didn't you, Hugh, about this?
Yeah, look, I don't think, even if I was going to die, I'd never drink warm beer.
Yeah, he's from Australia, so to let him off. Paul, thank you very much for your question.
Okay, thank you.
Great to have you on the show. Dominic, this one came in from Andy John, who said, if a comet were heading toward the Earth, it's often stated that the worst thing that could happen would be to break it up into pieces, because then you would compound the problem. So what do you think? Is it better to blast apart an Earth-bound impactor and then have lots of little bits to worry about, or is it better to just, it's coming, we can predict where it's probably going to hit, so we live with the consequences?
That's a serious question that NASA have been doing research into, and there are two approaches that you can take to avoid a comet from impacting the Earth. You can either give it a very small nudge and try and change its orbit so that it doesn't actually end up on a collision course with the Earth, but it skims past us. Or you can try and just blow the comet into smithereens so that none of those small pieces can cause very much damage. The problem is you need a very large explosion to break one of these comets apart. And if you, for example, fire a nuclear missile at a comet, then it's then going to become radioactive. And you may just end up with a lot of large fragments, each of which could wipe out a city of people and might be radioactive to boot. It really actually all depends how far away the comet is and how much warning we have and how much planning we can put into what the response would be.
We've heard from Mark Hampson via Facebook. NakedScientist.com/Facebook will take you to our Facebook page. He says, "Hi guys, I think it's not a good idea to blast it to pieces because the bits would break up and then they pound the Earth with lots of craters and rubbish." In other words, he's saying that there'd be a distributed attack, more likely to hit where there are people. Andrew Reitmeyer says, "Depends on how big the resulting rubble is. If the individual pieces were small enough, then they would all burn up in the atmosphere. I prefer the idea of painting one part of it and then using the extra absorption of light to steer it away from a collision course. If we could convince some clever engineers to paint a logo on it, we could also get some multinational company sponsorship for the whole action too." That's a clever idea, using sunlight to push it.
Yeah, you'd need quite a lot of warning because that would be quite a slow way of deflecting the comet. One of the principal problems, we don't have a very good idea what comets are made of and how structurally sound they are. So in terms of firing something at them to try and break them apart, we don't really know how they would fragment.
The point about sunlight, though, just in case anyone doesn't believe that that's feasible, there is something called the YORP effect, which is Yarkovsky-O'Keefe-Radzievsky-Paddock effect, which is photon pressure. So when photons, light packets, hit a surface, they impart a nudge or some momentum to it, and it is capable of moving big objects given enough time, because there was some modelling done for the asteroid belt, and a lot of the impactors that we think did away with the dinosaurs, you can retrace their history. They probably came out of the asteroid belt somewhere near Mars, and we think that some object got dislodged by the fact that you had this nudge from the pressure of light.
Yeah, and it's a very small effect, but the first detection of that was actually made only about 2 years ago, and there is an asteroid where it has been detected that the sun is putting pressure on it and pushing it out.
Dominic, thank you very much. Hugh, you've passed me a note here about Barnes-Wallis. Tell me more. Is this in relation to the asteroid question?
Yeah, well, I'm not a great expert on asteroids, but one thing that Barnes-Wallis found out during World War II was that dropping 40 250-pound bombs was not going to blow up the dams of Germany, but dropping one bomb, which was 10,000 pounds, would. So it strikes me then by a similar argument that it's probably better to have 40 small asteroids than one big one.
But also building on the point that was made in the original question, which is that more likely they'll burn up in the atmosphere. Or no, Andrew Reitmeyer texted in, didn't he, and said they'll more likely burn up in the atmosphere. So even if we had smaller ones, then they would impact a smaller impact because they're going to burn up.
And some, of course, will quite possibly miss the Earth altogether.
Terrific. You're listening to The Naked Scientist. Chris Smith, Diana O'Carroll, Dominic Ford. It's our Science Q&A special this week, so we're answering all of your science questions for you. John is on the line. Hello, John.
Hello, Dr. Chris. Good evening.
What can we do for yourself?
I've been thinking about the human brain and wonder whether it's developed at the same rate as the human body. If, for example, you were able to take a human brain of about 10,000 years ago and implant a representative cross-section of today's accumulated knowledge in it, would it be able to function as if it were a contemporaneous brain?
Well, that's a fantastic question. Diana, what do you think?
I think yes, of course. Someone who lived 10,000 years ago would be very capable of understanding all of the problems and issues that we have to deal with today. In fact, around 10,000 years ago was when humans were doing really incredible things like developing agriculture, which of course would have taken some intelligence, and doing what essentially is a modification of different grains and vegetables and things, which takes some foresight and some planning. And in fact, anatomically modern human, as it's known, first appeared 200,000 years ago, and there's no evidence to suggest that people then had different brains to the ones that we have now, although there's some arguments about maybe something happened around 60,000 years ago, but we don't really know for sure. But it looks like certainly 10,000 years ago people were just as intelligent as they are now.
How do we know that the brains of people 200,000 years ago were similar? Because brain tissue doesn't fossilise, does it? So how would we know that?
To be fair, it is a little bit of guesswork. There is genetic evidence to show that anatomically modern human hasn't... Well, we have evolved a little bit. There are a few mutations that have turned up over the last few 100,000 years. But if you take a fossil human and open up the brain case and look inside at the shape and the volume and the way that all of the little sort of veins and vessels are marked out on the inside of the brain case, you see that actually it doesn't look very different at all from what we find now.
So you're referring to the idea of this sort of endocast idea, where
That's right,
the sort of the shape of the skull can form a fossil on the inside where the brain would have been, leaving an imprint of what the brain must have been like, because the brain leaves its own imprint on the inside of the skull.
Yes, that's right. Your brain does imprint on the inside of your skull as you grow up, strangely enough.
Thank you, Diana. Matthias Thule got in touch on Facebook. Facebook.com/TheNakedScientists will get you there. He says, can you explain prions? Are prions living things like viruses or bacteria, or rather are they chemicals, and what are their effects on humans? Well, prions are the names given to these proteins which are in the nervous system and also elsewhere in the body, which are responsible for diseases like BSE, bovine spongiform encephalopathy, mad cow disease. In humans, the equivalent is CJD, Creutzfeldt-Jakob disease. These proteins are normal for the brain. We normally make them, but we make them in a shape or form called PRPC. This is a globular protein. It looks a bit like a ball of wool, and it dissolves really easily. No one actually knows exactly what it does in the nervous system, but it's a normal part of everyone's nervous system and other parts of the body as well, including the immune system. But for some reason, and probably because of the shape of the protein, this ball of wool can sometimes get tangled into a rigid fibrous shape called a beta-pleated sheet. And when it forms this beta-pleated sheet shape, then what can actually happen is it can make other ball of wool shape prions also convert into these rigid beta-pleated sheets. And from where you had one, you now have two. And two can convert two more, making four. And four can go out and convert more, making 8, and so on. And the whole thing grows exponentially. They'll build up in the brain, and they appear to be directly toxic to nerve cells, which is why you end up with this spongiform change in the brain, because you lose nerve cells and replace them with vacuolation or gaps or holes in the brain. It makes your brain a bit like Swiss cheese. And they appear to be able to transmit. So if you eat material which is contaminated with prions from a closely related animal like a cow, they can cross the species barrier, get into our body, go to the nervous system, and then they make the person develop BSE, or human BSE in this instance. So that's the prion story. It won a Nobel Prize for Stan Prusiner, who first came up with the idea. Diana, you've got a news story for us this week.
Yeah, that's right. Researchers this week have found the very cells that make up the internal compass of migratory animals. Now, these cells are able to detect the position of the animal in relation to the Earth's magnetic field. And they do this because the cells themselves contain a magnetic component. Led by Stephen Eder of Ludwig Maximilians University in Munich, the international team took cells from the olfactory organ of a trout, that's the trout's snout, and placed them in a strong, rotating magnetic field under a microscope. Now, because of the way in which these cells had been prepared, they were able to move freely as the magnetic field in which they were placed rotated. And when the magnetic field was applied, only the magnetic sensory cells would follow the movement of that field. Now, in previous years, researchers have found it rather challenging to identify these cells because the exact location is quite often a subject for debate, and because in order to work effectively, these cells have to be few and far between. When the team did identify the magnetic cells, they discovered that for every 10,000 epithelial trout snout cells, there were only about 4 of these magnetic sensory cells. The researchers believe that the cells contain the magnetic substance magnetite, which is about as magnetic as you can get in naturally occurring minerals. And the next question was, given that these cells cannot rotate freely when trapped inside the tissue of a living animal, how do they signal changes in the magnetic field? So in the trout cells, these crystals of magnetite are locked inside a cell membrane, and the researchers hypothesise that they cause the membrane to stretch when pulled in a particular direction by the Earth's magnetic field. So at a cellular level, it may be that this membrane stretching induces a signal to the animal, telling it which way is north. And that work is published in this week's edition of PNAS.
And they think that that effect is going to be sufficiently sensitive to pick up a magnetic field of the same strength as the Earth, which is, of course, important if it is going to use it for things like navigation.
That's right. In the experiment, they actually ran a field that was very similar to the Earth's natural magnetic field.
Isn't that fascinating? There was another paper recently that looked at, I think they were looking at pigeons' noses because people had said there's iron there, and they unfortunately found that it's nothing more than the avian equivalent of snot, because they found that the iron that was in the avian nose was in cells called macrophages, and they use iron as a cofactor in enzymes, and macrophages just eat bacteria and other infecting agents. So unfortunately for the pigeons, it wasn't to be. Thank you very much for that, Dinah. Here's a question for you, Dominic. This is Xaver Kober, who's in Germany. Hello.
Hello. I was wondering if the Higgs field is uniform throughout the universe, or if there could be natural circumstances in space that cause a distortion of the field.
Oh, wow. So it's hitting the Higgs hard. Dominic, that's a tough one for you.
Yeah, so I guess if we step back for a moment to what the Higgs actually is, I find this rather interesting because the problem which has been facing particle physicists for the last 20 or 30 years is looking at the zoo of the strange particles we have in the universe, the quarks that make up protons and neutrons, the electrons, the photons, neutrinos, etc., and wondering whether these are just a random set of particles we have in the universe or whether there's some pattern to their properties. And one problem has been explaining why some of these particles, like quarks, have mass and others, like photons and neutrinos, don't have mass. And what Peter Higgs did in the 1960s was to show that although these particles don't form a neat pattern just with the ones that we've seen, if you have one more particle, which is the Higgs boson, then you got a very nice pattern which could explain why some of these particles have mass and others don't. And it's all to do with whether they interact with the Higgs boson, which creates this Higgs field, and mass is given to a particle by its interaction with that Higgs field. Now, in terms of the properties of that Higgs field, I think we're going to learn a lot more about that from the LHC in the next few years as they study this particle that they seem now to have discovered. I think the general thinking is that the Higgs field is constant throughout the whole universe. It's created by Higgs bosons popping out of the vacuum. But I'm sure we will learn a lot more about it in the next few years.
You're listening to The Naked Scientists. Chris Smith, Dominic Ford and Diana O'Carroll. We're answering your science questions, including some very tough ones. Carol's on the phone. Hello, Carol.
Hello, Chris. I just wanted to find out, dinosaurs breed, and when they a temperature, a certain temperature, then you only have females, or at another temperature only have males. Crocodiles breed, and that's what happened with crocodiles. But maybe when the Earth warmed up or cooled down too much, this is what happened to the dinosaurs, and maybe they couldn't reproduce.
Wow, what a great question. So if the world's temperature changed dramatically, Diana, could this account for the demise of the dinosaurs?
Well, yes, temperature certainly has been linked to the demise of the dinosaurs, but normally I think people associate it with the destruction of food availability, or plants could no longer grow in colder conditions. So what you're talking about is something called temperature-dependent sex determination, which happens in crocodiles. Now, normally, and turtles as well, normally what happens is when eggs are incubated at lower temperatures, you tend to get more males, and when they're incubated at higher temperatures, you get more females, although there are some variations on this. Now, we know that TSD, temperature-dependent sex determination, happened about 300 million years ago, so that is kind of when the dinosaurs were around, so it's possible that dinosaurs did this. But birds, which are descendants of dinosaurs, determine their sex genetically. It's nothing to do with temperature. So at the moment, we can't really argue that dinosaurs did have this way of determining sex. And the other sort of counter-argument is that crocodiles and turtles have survived the asteroid collision. Obviously, the temperature didn't affect their breeding. There's evidence that dinosaurs actually purposefully laid their eggs in geothermally warm places so they could actually control the temperature of their nests.
Natural incubator.
Yeah, exactly, that kind of thing. So the TSD hypothesis is an idea that could potentially be true, but I think at the moment it seems quite unlikely.
Distilling the best science. The Naked Scientists.
It's The Naked Scientists. It's our science phone-in. Any science question goes. Don't forget Hugh Hunt, who is the Aussie guy and doesn't like warm beer. He's here to do an experiment with us. He will prove to you why Frank Lampard was sorely disappointed during the 2010 World Cup when his ball went into the goal and came back out again. If you want to have a go at this, and he will explain the engineering and the physics points of this when we do the experiment, go and grab yourself a bouncy ball. You'll need a table, and Hugh, just very briefly, tell people what they need to do to demonstrate the effect for themselves that you're going to show later.
Yeah, well, you have your bouncy ball and the table. You bounce the ball under the table, and you'll see what happens. The ball hits the ground, hits the underside of the table, hits the ground again. Have a look what happens next.
And we should challenge you, can you get the ball to go all the way under the table and out the other side? Now, which way do my eyes go when I am telling the truth? Have you heard this claim that people, when they're lying, look in a certain direction?
I have heard this claim, actually, yeah. I think, is it up and to the right and you're supposed to be lying? Something like that.
He says, looking fiercely off to the left. This is a claim, and it's put forward by practitioners of what's called neural linguistic programming, NLP. And this is a collection of psychological techniques that's been pulled together to help people communicate better. And the thing is that they say, and it's largely based on work that was published in the 1960s by Paul Bakken, who was a psychologist working in the States. He had this idea that there are these areas of the brain called the lateral eye fields, and if you have a certain part of your brain working very hard, then some of the activity could spill over onto these lateral eye fields, and they provoke eye movements. And because the brain's crossed over, right side controls left, if you make the right side more active, it'll make you look to the left, and so on. So if you invent things, then you're more likely to be using the left side of your brain, and that will make your eyes look to the right, and so that's the hallmark of a lie. Well, the actual thing is that whilst they've claimed all this and they teach all this, there's not really any evidence whether or not it's true. So Richard Wiseman, who's a researcher at Hertfordshire University, decided to put this to the test and has published some very interesting work on this in the journal PLOS ONE this week. And he did 3 experiments on students. Best way to do research, use students, because they'll do anything for a free lunch, won't they? So they did 3 experiments. In the first experiment, big group of students, and what they asked them to do was to take a mobile phone, go into an office, and they did this twice with each student in random order, either put the phone in the drawer in the office or hide it in their pocket. They came out of the office. They were then put to a second person who was then going to interview them and ask them what they had done with the phone. And they had been told at the start they had to always say the phone had been put in the drawer in the office, and they had to be as convincing as they could be. And then another group of individuals looked at videotapes of the students telling the interviewer what they'd done with this phone, and they were coding it for whether they were looking right or left according to whether or not they were lying or telling the truth. They then compared the truth situation for the student with the when they were lying situation. They found no bias in their gaze whatsoever. They then did another experiment, because some people have said, well, people who do a lot of this NLP work are highly trained and they therefore know what they're looking for. So they took another group of individuals, trained half of them in what to look for, the other half were just controls, and they then said, OK, now look at these videos of the students in Experiment 1 and tell us who you think is lying. And again, they were no better than the controls at spotting the liars, and the only thing that the training did was to make them have greater conviction as to whether or not they were right or not. And so then they said, well, just in case, because hiding a mobile phone that someone's given you is hardly a strong test of whether or not you really want to be found out or not. So why don't we go to press conferences, videos of press conferences, where people have really got something to lose if they get it wrong. And so they took 52 videos of people who were either searching for a lost relative and were telling the truth half the time, or the other half the time were subsequently proved to be frauds. They'd either murdered somebody and were saying, please bring them back, or they'd hidden them or helped them to abscond or something like that. They then coded the eye movements of those people, found absolutely no upward left or upward right gazes. So, as they conclude at the end of their paper, these results provide considerable grounds to be sceptical of the notion that proposed patterns of eye movements provide a reliable indicator of lying. As such, it would seem irresponsible for such practitioners to continue to encourage people to make important decisions on the basis of such claims. So stop looking up to the left.
I think it's interesting that sometimes people can be described as good or bad liars. So do you think this study helps us make any inroads into that? I mean, it's obviously eye movement has nothing to do with it.
Do you mean in terms of some people are just very good at picking up the body language that goes with lying? Because there's certainly a body language that goes with lying, and people also change the coloration of their face when they lie. There's scanning technology been implemented at airports which looks for changes in blood flow around the eyes, which intensifies when people tell porkies. And I think this is being used quite universally.
Oh, so there are things that can be detected then in lies.
Yeah, absolutely.
Fantastic.
So, Dominic, what have you got for us this week?
Well, a team of astronomers using the Very Large Telescope in Chile believe that they may have made the first ever observations of galaxies that have no stars in them. And this is the work of Sebastiano Cantalupo and his colleagues at the Kavli Institute for Cosmology in Cambridge.
A galaxy with no stars? I thought the whole point of a galaxy was it did have stars.
Now, you might think that would be quite a boring galaxy, but in fact these are objects that fill a gap in our theoretical models of how galaxies form. The problem is that models predict very efficient star formation early in the universe, and that means that most of the gas available to form into stars will have formed into stars very quickly in the first few billion years of the universe. In fact, what we observe is that star formation continued for 5 to 10 billion years after the Big Bang and is still going on today, 13.8 billion years after the Big Bang, albeit at a rather reduced rate compared to what was happening a few billion years ago.
So these galaxies that have no stars, is that because they're just aggregations of gas, but it hasn't got together to form a star yet?
That's right. The conditions don't seem to have been right to trigger the gravitational collapse that would make this gas fall into stars. So what you got is pristine gas, which has come out of the Big Bang, which is just sitting there in a diffuse cloud. Now, what the theorists think happens is that these gas clouds then later fall into larger galaxies, which are forming stars, and provide fresh fuel that those galaxies can turn into stars. And this allows the star formation process to be prolonged through cosmic history, as we have observed.
And how many galaxies like this do you think there are? Are these a really big exception, or are they quite common?
The problem is they're very difficult to observe, because we see galaxies by looking for the stars in them. Now, if you haven't got any stars, you haven't got any optical light to pick up. So what this team have done, they have looked in the neighbourhood of a very bright quasar. This is one of the brightest objects in the universe, and it puts out a really prodigious flux of ultraviolet radiation. And this radiation field is so strong that it excites the hydrogen gas in these gas clouds, which then re-radiates that light in a line called the Lyman alpha line. So they're looking for a fluorescence of these galaxies based on the radiation they're seeing from this nearby quasar. And around this quasar, they've seen 98 of these clouds. So it's not just one, they're repeatedly seeing these clouds around this quasar. The problem is this is all one local neighbourhood. So we had to ask, is that neighbourhood typical, or is there something odd about this part of the universe? So the next question is to go and look elsewhere in the universe and see whether you see similar numbers of them. And I spoke to Martin Heyholt, who is one of the authors of the paper, this week, and he told me that they are hoping to put in observing proposals to look around other quasars and bright objects and see what they see in those neighbourhoods.
Thank you very much, Dominic. Now, antibiotics and vaccines save lives, but to do so they usually need to be kept cold. And this can be a bitter pill to swallow for third world countries that just can't afford the necessary refrigeration, despite having probably the most to gain from these sorts of treatments. But now that might be about to change thanks to a breakthrough by Tufts University scientist David Kaplan, who has discovered that wrapping vaccines and antibiotic molecules in a layer of silk can keep them in pristine condition for months, even at temperatures above 40 degrees C.
My lab has studied silk for over 20 years, so we've gotten to know the protein very well. We've learned how to clean it up, how to purify it, and how to use it in medical devices and medical materials of all kinds. And as a result of that, we've also studied the ability to put things like enzymes into silk and show that they're inherently very stable under those conditions. And that led us to hypothesize if an enzyme, which is a protein as well, is stable in silk, perhaps there's broader utility to entrap and stabilize other molecules like vaccines where there's a real need and a real challenge.
When we say silk, it implies a scarf or a tie or something. Are we really talking the same stuff that you would weave into a silk scarf or a silk tie when you're doing your work?
So yes and no. We're certainly talking about the same source material. So the material we start with comes from the textile world. And that's a great thing because that means there's a huge supply of the material available, which makes the costs relatively low. The downside is you would never introduce textile silk into the human body. You'd have severe problems with inflammation and you would have difficulty. And so to use the silk, we and others have learned over the years how to get rid of all the proteins on the silk that otherwise would cause inflammation. And when you do that properly, you have a very nice material that's compatible with the human body and in fact has been used and FDA approved in a number of medical devices already.
So you don't get reactions with the immune system, for example, because it's a foreign protein. So you'd think if you put that into the body that the body would recognize that as not part of it and you'd get a reaction.
That's right, and yet the reactions are very, very tepid, and so you don't see any kind of major problems that you'd expect. In fact, all the studies published around the world from our lab and others always show that of all the approved degradable polymers used in medical materials, silks always tend to be the lowest in terms of any inflammation or immune response. So it has to do with the chemistry of the silk. It's a very hydrophobic molecule. It has to do with the fact that it degrades in the body very slowly, and I think the this combination of features helps to give this very low response.
So what did you do? You took some silk that had been prepared in the way you say, and then mixed them with antibiotic or even viruses to see what the silk would do.
That's correct. We create solutions of the silk protein in water, and once you have that, we can add in essentially any bioactive molecule that you would like. In this study, we showed with vaccines and antibiotics, and then you have to process that solution into a stable material format, and it can be in the form of a film, it can be in the form of a fiber, a gel, or we make things like microneedles, sort of like a Band-Aid that can administer through the skin.
And when you do that, what impact does it have on the stability of the agents that you invest in silk in this way?
Remarkable improvement in stability, not just under refrigeration conditions, but even at temperatures as high as 45 degrees centigrade. And even over 6 months, you still retain the far majority of the activity of these vaccines, which is quite remarkable, I think.
Compared with, had you not had the silk there, the activity
That's
would
right.
by that time have just gone to zero.
That's correct. You would have lost all activity.
Do you know how it works?
In the paper, we also discuss a little bit on the mechanism, and in brief, what we find is there's clearly some interactions between the silk protein itself and the proteins on, at least in this case, the inactivated virus that we use, that appears to essentially pin the protein together and prevent it from denaturing or aggregating and losing bioactivity. And that's coupled with a low water content in the silk. And then the last point is silk is dominated by these very, very small nanoscale hydrophobic domains. We call these beta sheets. These are the crystals. And because they're very, very small, there's lots of interfaces, lots of room for vaccines and other molecules to sort of pin up against these structures and become immobilized and less prone to be inactivated.
It sounds like a pretty awful example for me to give to you, especially when we're talking about medical things, but I've won enormous amounts of money in bars by betting people I can bend a cigarette so that the one end will touch the filter end, and the way you do it is by wrapping it in a £5 note. And having the investiture of the note around the outside of the cigarette means you can make it do unfeasibly bendy things. Are the particles, then, that you're putting into the silk, are they effectively being stabilised by this enwrapping or this ensheathing in the silk, and that just stops them falling apart?
I think it's a great way. It's two things. One is exactly what you say. I think it prevents them falling apart or falling into the misshapen form so they're no longer active. And the other is it prevents them from aggregating too much because there's not a lot in one spot. And so I think that combination helps a lot.
How do you get the particles away from the silk again, though? So when you actually want to use the antibiotic or you want to metaphorically smoke the cigarette, when you want to administer the vaccine or whatever, do you need to get it away from the silk, or is that not necessary?
There are many options. The three we most commonly talk about, one is you can resolubilize the film with the vaccine in it and inject that, and silk has been injected before. It's safe to use. There needs to be more human clinical trials done, but that would be the easiest format, and I think that would be very attractive. If you don't want to do that, you could certainly solubilize and then separate the vaccine from the silk. And the third, which we happen to like the best, would be when you fabricate the films, you fabricate them in these microneedle formats that I mentioned before, and these become essentially a film as a Band-Aid strip with little pinpricks on one side. And so you can simply put that on your skin, and the vaccine would then get through the skin based on the dissolution of the silk under the skin. So you never have to separate it from the silk. You can just use it as is, as an intact device. And so that's very attractive because that's sort of something you could ship around the world and use on demand.
Isn't that amazing? You can keep these things viable for months at higher than body temperature just by mixing them with some silk. That was David Kaplan from Tufts University in the US, and he published that work this week in the journal PNAS. Dominic, got a question here from Luke, and he says, in regards to the redshift and blue shift of stars to measure their movement away from us or towards us, if the information we have to recognise distant stars is just the light emitted by them, how do we know that the redshift or the blue shift isn't just the natural colour of the star rather than its movement?
Well, stars certainly do come in a wide variety of different colours. Hotter stars will tend to be bluer than cooler stars like Betelgeuse, which are comparatively red. But when you're looking for the redshift, looking at the frequency shift which is associated with the velocity of that star, what you're looking at are spectral lines. These are very specific wavelengths in the spectrum of that star where particular elements produce light in a very small range of frequencies, and this produces a bump in the spectrum which is always in exactly the same place. And what you see when a star is redshifted is that characteristic bump is shifted to a different frequency, and you can be sure it's the same bump you're looking at because they form a pattern across the spectrum of different elements emitting at different wavelengths.
So you basically know if your hydrogen bump is shifted a little bit, that it's definitely hydrogen, it's just offset by a certain amount, and the amount it's going to be offset by is proportional to the amount the star has been red-shifted or blue-shifted, and that tells you how fast it's moving away from us.
Exactly it, yes.
Dominic, thanks very much. Diana, Andrew Steer is wondering, is there a gene for liking Marmite?
Quite possibly.
You either love it or you hate it. So it does seem to elicit very extraordinary and profound reactions in people, doesn't it?
Actually, do you know what? I'm going to say that I'm ambivalent towards Marmite in small quantities. Actually, there is a gene which determines how sensitive people are to compounds called phenylthiocarbamide and propylthiouracil. And you find these bitter compounds in things like cabbage and rapeseed. Now, some people are very sensitive to these bitter compounds and some can't taste them at all, and this is genetically determined. Apparently it's sitting somewhere on chromosome 7. It's thought that maybe the people who can taste these PTC-like compounds are very sensitive to bitter things like grapefruit, tea, coffee, as well as cabbage and kind of what are they called? Cabbagey plants. Cruciferous, that's one. I know it had a cross in there somewhere. So it may be that Marmite is related. It's got that bitterness element in it.
Dominic, here is one for you. John in Norfolk has said the photons that make up light and travel at the speed of light are massless. So how could a massless object have an effect on matter? This is referring back to the point you were making about pushing an object like a big asteroid out of the way using a stream of light.
Yes, now this is actually a very common misconception, because at school, of course, you're taught a lot of Newtonian physics where something without mass can't exert a force, it doesn't have momentum. But in fact, a photon is a relativistic particle, and in relativity, energy and mass are equivalent to one another. So although the photon doesn't have any mass, it has momentum still, which is associated with its energy, and that's significant because the photon is travelling at this relativistic speed of the speed of light. So Einstein's theory of relativity has completely taken over from Newtonian physics, and that explains how the photon can have this momentum which it can impart to an asteroid.
Thank you very much, Dominic. You're listening to The Naked Scientists. Chris Smith, Diana O'Carroll, Dominic Ford, answering your science questions. Mark in Essex is wondering what the origin of circumcision is. I don't know the answer to that, so if anyone knows how the practice got started, I think in terms of history, it's very, very ancient as a practice, though, isn't it, Diana, if you look back archaeologically? Do you know?
I have to say I'm not an expert. I'm certainly not an authority on that particular practice. And medically, I'm sure that people would have tried to do it where it was necessary, yeah.
And certainly also, culturally as well, for many thousands of years. And now, with a roundup of some other news science stories that are hitting the headlines this week, including how Batman's cape isn't as effective as he would hope, here is Mira Senthalinga.
2 proteins have been identified to help fight and potentially treat the neurodegenerative condition Huntington's disease, according to research in the journal Science. Patients with the disease have a gene mutation resulting in misfolded forms of the protein HTT, which then builds up in their central nervous system, causing the progressive deterioration of muscle control and cognitive decline. But now, Albert Laspada from the University of California, San Diego, found that elevating levels of the proteins PGC1 alpha and TFEB in patients with the disease helped prevent the buildup of mutant HTT proteins, preventing their aggregation and resulting neurotoxic effects.
There are features of Huntington's disease that are shared by more common neurodegenerative disorders like Parkinson's disease. So if we can develop therapies based upon these strategies, they should not only be applicable to Huntington's disease, but also be applicable to Parkinson's disease and perhaps other neurodegenerative disorders.
Smart materials with the ability to regulate their temperature have been developed by scientists at Harvard University, publishing in the journal Nature. Modelled on the process of homeostasis in the human body, whereby body temperature is maintained at 37 degrees, these homeostatic materials consist of a surface gel layer which, in response to a drop in temperature, activates the movement of catalyst-containing structures into a second reactant layer where the catalyst initiates an exothermic reaction, causing the release of heat. Joanna Eisenberg led the team, who hoped to use this technique to control a wide range of environmental conditions.
The prototype material shows that we can maintain a constant temperature. But in fact, the same strategy can be adapted to create materials that maintain constant glucose level in the bloodstream or pH in water supply. We're really thinking now of a whole range of materials that are capable of autonomous self-regulation.
Altruistic individuals have more grey matter in the region of their brain responsible for empathy. Writing in Neuron, Yosuke Morishima from the University of Zurich used fMRI techniques to monitor brain activity in human volunteers as they answered questions about splitting money between themselves and others. His team found that the volume of grey matter found in a region of the brain known as the temporoparietal junction and the level of activity there was a strong indicator of how altruistic an individual would be.
When you look at that other people, so we can't tell whether that person is really nice or really generous or selfish, but our study would partly tell us about individual private information which cannot be transparent. And also, some behavioral studies have shown that people who are living in a really large society tend to behave more altruistically compared to the people who live in a small society. Maybe we might be able to elucidate the cultural influence on our brain and on our behaviors.
And finally, the cape used by well-known superhero Batman to glide from tall buildings would, in reality, send him crashing to the ground at high speed. Physics students at the University of Leicester calculated that the 4.7-metre wingspan of Batman's cape, seen in the recent films by Christopher Nolan, which becomes rigid as an electric current passes through it, isn't big enough to enable the caped crusader to glide to safety when jumping from a building 150 metres high. In fact, the team led by David Marshall worked out that the hero would hit the ground at 50 miles an hour.
Batman's cape is maybe not as effective as it could be just because it's too small. When you look at it compared to, say, a hang glider, it's about half the size that it needs to be to keep Batman aloft. And it's okay for moving. He can get to about twice as far as he can fall, which is sufficient for getting between buildings. But by the time he gets there, he'll be travelling at around about 50 miles an hour. So there's a few different ways that he could fix this by getting a bigger cape, or he needs some sort of active propulsion system, such as jetpacks. Really, Batman needs to find some better way to deal with this.
And their paper, Trajectory of a Falling Batman, was published this week in the University of Leicester Journal of Special Physics Topics.
Mira Senthilingam with our Naked Scientists Newsflash. Back in time now, almost 50,000 years to the final days of the Neanderthals and the rise of modern man. Research published in the journal Science has revealed the oldest known cave art in Europe, and it might not have been painted by humans. Richard Hollingham has been to the University of Bristol to talk to the archaeologist who led the project, Alistair Pike. As they didn't have a cave handy, Alistair projected the art onto the wall of a lecture theatre so they could get an idea of how it looked.
We're looking at the panel of hands. It's a part of a cave called El Castillo Cave in northern Spain, very close to Santander. And this part of the cave, maybe 41,000 years ago, was decorated by people putting their hands against the cave wall and then blowing or spitting pigment to create these negative hand images.
How old are these?
Next to the handprints there are some red dots, and one of those red dots is at least 40,800. But because we can see that they were made in the same technique, they don't overlay each other, we think actually the handprints were made at the same time.
What does that mean then? I mean, it sounds an awful long time ago, but that has particular significance.
Yes, well, first of all, it's at least 15,000 years older than we previously thought the art in this cave to be. But it dates from around the time when modern humans first arrived in Europe and the Neanderthals begin to disappear. But because we're dating these deposits on top of the art, we don't actually know how old the art is. All we know is it's older than 40,800, and therefore it might have been made by Neanderthals.
Would that be the first?
Absolutely, or certainly painting. This would be the first example of Neanderthal painting. So you can look at the fingers, the handprints of Neanderthals, if indeed this is the case. But we do know that Neanderthals, maybe 50,000 years ago, were making art-like objects in other parts of Spain. So we find things like shell beads to use for body adornment. We find shells that have traces of pigment in them that look like they might have been used as a sort of cosmetic, even.
So once again, Neanderthals turn out to be a lot brighter, a lot more advanced, if I know archaeologists hate using the word advanced, but that than we perhaps thought.
Well, if this genuinely is Neanderthal art, and we haven't yet proved it beyond all doubt, because conceivably it could have been made by modern humans a matter of a few hundred years after they first arrived in northern Spain. But if it does turn out to be Neanderthal, then it's showing that Neanderthals have the cognitive abilities rather similar to modern humans. So we've narrowed the gap in the difference between them.
But even modern humans, when they started turning up in Europe, they didn't have a culture of art before that, is that right?
Well, that's a very interesting question because, in fact, in Africa, we do find art objects around 70 to 100,000 years ago, which include little bits of engraved red ochre minerals. We find beads and bead necklaces, and we find engraved ostrich eggshells. But the earliest paintings in Africa are only around 25 to 27,000 years ago.
So a lot more recent than the ones here, for instance.
Absolutely. So it looks like the tradition of painting caves started in Europe. And that's a really interesting question to ask. Why should it be that humans should start painting caves in Europe and not in Africa when they'd been making art objects in Africa for the previous 50,000 years? And we think we've got an idea about why this is, and that is actually the presence of Neanderthals. And we find just after humans arrive in Europe, we find the first examples of musical instruments, of figurative sculpture. We may have found the first example of painting. And the difference between Africa and Europe at this time was the presence of Neanderthals. So it might have been that in order to compete for resources with Neanderthals, modern humans had to organise themselves differently socially, and art may have been one of these innovations that allowed them to create a group identity and therefore compete with Neanderthals.
So if we look up at this image projected on the wall of the lecture theatre here, you've got these handprints and this shadowy image of a bison or something, and concealed by this calcium deposit over the top. How on earth do you go about finding out the age of this without damaging it?
Well, the key to actually being able to date these things is that calcium carbonate deposit that you mentioned. And we can use the radioactive decay of uranium, which decays to thorium, to work out when these things formed. And it's the measurement of the thorium to uranium ratio that tells us how much time has passed since the precipitation of the calcium carbonate. And since these formed on top of the paintings, we know they must have been older than the dates that we're measuring.
So actually, it's relatively straightforward thanks to the material that's obscuring them.
Absolutely. Some people might think it's a shame that you can't see all of the art, but it's thanks to that layer that we can actually obtain age information about the paintings.
Now, we talk of this as prehistory, but I suppose this really was the first history, particularly as people came back. It's a record, really, of humanity.
Oh, absolutely. And there are some studies that have actually looked at some of these symbols, and they find groups of them reoccurring in different caves all over Europe. So, in fact, we might be looking at a form of language here.
So, really, this is the start of so much.
It's the beginning of the modern period for humans, if you like.
Archaeologist Alistair Pike from the University of Bristol. And you can hear more of that in the Planet Earth podcast. You can find that by going to thenakedscientists.com/Planet Earth. Now, on this question about the history and origins of circumcision, Trish in King's Lynn has got in touch and pointed out that there are various aspects of the Jewish faith with the rite being carried out on the 8th day after birth because coagulation factors have peaked by then. And so there must therefore be Jewish ancestry to this. I mean, I think everyone knows that. But if we look back further in the history books, what have your sort of proddings and pokings with Wikipedia and so on, what have you flushed out?
Well, it looks like circumcision has been attested historically, at least amongst the Egyptians, and that would have been around the 3rd millennium BC. And it seems to be something that's to do with cleanliness, at least amongst the ancient Egyptians. And then a few millennia later, Herodotus was writing about the Egyptians, and he also said that they were regularly circumcising themselves, but he described it as a rite of passage, as a way of marking the transition from childhood into adulthood. So perhaps the meaning of circumcision had changed a little bit by then. And I think the fact that people in different cultural groups, people in different areas of the world are practicing circumcision or were practicing circumcision explosion implies that it might be something that's gone on far longer than our historical records would imply. It could have been happening millennia and millennia ago, but unfortunately, the evidence for it doesn't really.
It doesn't fossilise well. Not many fossilised foreskins, I suppose.
No, I can't say I've ever heard of one that's.
I mean, of course, today we still continue to discover things about this because now it's been shown to have quite a dramatic effect on HIV, maybe 80% reduction in risk. And the same benefit transfers to HPV, the human papillomavirus, which causes cervical cancer and penile cancer and warts. So it does seem to make quite a big health difference. So maybe Herodotus was right after all. Yeah,
I mean, it's a very interesting and contentious question, the difference between the medical benefits and the cultural associations that come along with it. And as we've seen in Germany recently, it's quite an interesting discussion that can provoke all sorts of interesting and emotional responses.
And a very quick one, questions coming from Stephen, who says, Dominic, why do copper and aluminium conduct heat so much better than other metals, and why do they conduct so well?
It's all about having charge carriers in the metal which can conduct both electricity and heat, and so if you put energy into those, they flow through the metal and conduct both heat and electricity through it.
In other words, so if something's got electrons like copper, loads of them that can move around very freely, when you make it hot, they're going to vibrate a lot and move around, carrying those vibrations and transmitting those vibrations, i.e. heat, through the material in just the same way as they would migrate in an electric field.
Exactly, they're not bound to atoms, so they can move all the way through the material.
Dominic, thank you very much. Now, I've been looking forward to this, which I'm going to hand over to Diana, who's going to get playing with some balls. Off you go.
That's what I like to do. Well, here I am. I've got Hugh opposite me, and he's holding a couple of balls as it goes. And there's also a little table that's been set up. So what are we going to do with these two objects?
Right, the bouncy ball I've got here, I throw it under the table, and it's going to bounce 3 times, once on the floor,
Yep.
once under the table, and then back on the floor again.
Yep.
And here I go.
Okay. So you threw that in my direction towards me, and instead of coming out towards me, it's gone back to you.
Absolutely.
So why's that happened? Well, this isn't right.
It isn't right. Well, it doesn't seem right, but it is, in fact, exactly what you would expect to happen if you sit down and think about it. The first thing is, imagine just what happens to the ball after it bounces on the ground.
Okay.
So if you've got a friend, just bounce the ball towards that friend. I'm bouncing
Okay,
this
so
ball
he's got
towards...
a slightly larger ball here, which hopefully will bounce a bit slower.
And I'm bouncing it towards Diana.
Yep.
And what do you notice, Diana?
Okay, it was spinning as it sort of came towards me.
Well, it wasn't spinning when I threw it.
No.
It's spinning after it hits the ground. It's coming in at an angle on the ground. It starts to spin. Now, that's what you expect. If a plane is coming to land and the wheels are not spinning, what do the wheels do immediately as they touch the ground? They start to spin. Well, why shouldn't the ball start to spin? Right, now I've got a spinning ball and it's heading up towards the underside of the table. Well, we all know that if you've got a ball with a bit of spin on it, Shane Warne and some of the best ever bowlers. I better not talk about cricket at the moment, but never mind.
We've only got a few minutes on this.
Talk about tennis, because that's okay.
Yeah, but there aren't the Australians playing tennis either. So if you put some backspin on a ball, then... You see what happens if I put backspin on that ball?
It bounces back towards you.
Yeah, and if I put topspin on the ball, then it goes over towards you, you see.
Yeah.
So the idea is you throw the ball on the floor, it starts to spin. Okay. Now that it's got some spin, it's backspin on the underside of the table, so it comes back towards me. And it's one of these great things that if you actually stop and think about it step at a time, it makes perfect sense.
I see. So what are the real-world applications of this, then?
Well, the application's a bit hard to find. But understanding spin is very important, gyroscopic effect and all that. But there was an episode in 2010 in the World Cup. Frank Lampard's goal was disallowed. It's exactly the same as this, because if you look at the replays of it, the ball hit the crossbar, started to spin, went down, hit the ground inside the goal, but because of the spin, it came back out again.
So that was just enough to confuse the linesman and the referee. Obviously.
Yeah, maybe we need goal line.
Because they're going to put the new technology in to
Well,
stop
the new
this.
goal line technology should, with any luck, pick that up.
Yeah.
Because, I mean, the same science is manifest. I know I said tennis and you said, well, there's no Aussies. But the thing is that when you see those balls go flying through the air and then they suddenly just nosedive just inside the touchline, and the person then scores this point and then says, I want to appeal this, that's just the same thing, isn't it?
Well, it's kind of different. I mean, the spin in the air is this Magnus effect, which is the effect of the aerodynamics, pushing the ball down if you've got topspin and hovering the ball up if you've got backspin. Now, the impression is that it suddenly dives, but it's just that the ball is coming down at faster than g because of the topspin and the downforce due to Magnus effect. It's very deceptive, and that's what a good tennis player is doing, is trying to create motions on the ball that deceive you.
But one other point I did hear someone make about this is that when the ball is travelling really fast, the air can't stick to the surface very well because of turbulence, whereas when it slows down a little bit, then the air finds it easier to stick on, and then this Magnus force kicks in and it pulls the ball down because of the spin, and then it nosedives really quite dramatically, and you've got 15 seconds to come back at me on that.
It's certainly true that speed makes a big difference, and we know about swing on a cricket ball, reverse swing and so on. It's very sensitive to speed, humidity, all sorts of things.
Hugh Hunt from Cambridge University. We've got an example of the physics of spin that he was talking about on our website for you to look at, nakedscientist.com/kitchen science. Now, Hannah Critchlow has been worrying about what she had for dinner last night in our question of the week.
The Naked Scientist's Question of the Week, brought to you in association with the How to Wisman Foundation, supporting science and education from Alpha to Omega.
This week we move our questioning eyes down the digestive tract.
Hello, my name is Klaus Goffeng. I'm from Gothenburg, Sweden. Much food-related illnesses come from contamination by intestinal bacteria due to poor hygiene in meal preparation. So the obvious question is, will the person whose bacteria got into the food be sick as well?
So, can your own bowel bugs make you sick, or can they only make other people sick? According to Professor Liz Sockett at Nottingham University, the mucosal lining of your gut contains immune cells, which make antibodies, which will attack and neutralise specific bacteria. The immune system will remember seeing the specific bacterium if it reinfects. So, for the second exposure, the immune system will probably neutralise and kill the bacterium before it can multiply sufficiently to cause disease. But some food poisoning isn't caused by the bacteria growing in the individual, but by the toxins produced by the bacteria in food that has been poorly stored. The toxin damages your intestinal wall lining so quickly that you haven't got the time to mount an immune response to protect yourself. So immunity cannot protect you, and you could show symptoms on repeat exposure to the toxin. Staph aureus, for example, which can be found on the skin where it causes boils and spots, if that gets into poorly stored food, produces toxins which are heat and acid stable. So the bug may not survive in the cooking process and the acid environment of your stomach, but the toxin does, and it can poison your intestine, causing diarrhoea and vomiting. Harry Flint, Professor of Rowett Institute of Food and Health at Aberdeen University, explains.
Intestinal damage and diarrhoea caused by the huge quantities of toxin present in the food and produced by the bacteria multiplying in the food can affect you even if you have acquired immunity to the bacteria.
And this has caused quite a contagious conversation amongst all of you on the forum. Evan AU comments that some people are symptomless carriers, so they do not clear the microorganism from their system. Instead, they continue to shed the pathogen indefinitely. One of the most infamous cases was Typhoid Mary, who had no symptoms of typhoid fever, but managed to infect many people in her occupation as a cook. And some people died. So, can you get sick from your own intestinal bacteria? Due to acquired immunity, the chances are low, but ingesting bacterially made toxins can cause a repeat illness. Now, making a movement towards Mars.
Hi, this is David Gould in Dublin, California. If scientists conclude that Mars is lifeless, will they decide to introduce life in order to terraform the planet?
So, could we introduce life onto Mars? What do you think? Let us know by tweeting at Naked Scientists, write on our Facebook page, email chris@thenakedscientist.com, or join in the debate on our forum, which is at nakedscientist.com/forum.
Hannah Critchlow. She'll be back on the 5th of August when we look at the Curiosity mission, which is landing hopefully on Mars that day. That's it for this week. Thank you to Hugh Hunt, who joined us to do our experiment, and also Dominic Ford and Diana O'Carroll, and our production team, Mira Senthalingam and Tom Simpkins. Join us next time for a look at the science of flight.
The Naked Scientists podcast comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC, the STFC, the Natural Environment Research Council, and UK FAST. For more cutting-edge science, join us online at nakedscientists.com.